All right, I'm gonna set you up with a battery. Here's my battery, and I've got some resistors. Yep, I'm gonna have 3 of them. See how hard it is for the current to get through those resistors because they're so bumpy? So I've got resistor 1, and resistor 2, and resistor 3, and over here I've got the voltage of the battery, and there's probably going to be a current as a result since I've hooked everything up. My question is, this is our question to start off the day, what is the same for all 3 resistors? These resistors are experiencing one thing that is the same, and I want you to find out what it is. So pause, figure it out. I'm seriously not going to go on until you think about it. What is the same for all 3 resistors? Oh, you thought I'd just go on, did you? Huh, no. What is the same for all 3 resistors? Figure it out. I'm really not going to tell you. You have to figure out what is the same for all 3 resistors. Oh, good job. Right. The same for all 3 resistors will be... Ha! You thought I was going to tell you? No! Figure it out! What's the same for all 3 resistors? Okay, so if that is the same for all 3 resistors, we can write the following statement. Now, that's cool. If... Nope. What about... Nope. What about... Yeah, because there's no way for current to back up in any of these suckers. You're going to have the same current going through this one as you do through that one, as you do through that one, because they are in a series path. They're in a series path, so the current going through them has to be the same through each one of them. If I were to write a little bit of V as IR, are you ready for some V as IR? Here's what I'm going to say. I'm going to say that V1 is the voltage between that side and that side. So to show this, I could hook up a little voltmeter schematic to there and to there. And over here, I could hook up a voltmeter that's going to read me V2 from there to there. That's the voltage drop across resistor 2. And then V3 is the voltage drop that I get when I look between one side and the other side of this resistor right here. Now, you would certainly agree that V battery is equal to V1 plus V2 plus V3. And you know also that V battery is equal to I total times resistance total. Some people like to call this the equivalent resistance of the circuit. Now, do you think that the resistance of this circuit is more than if we just had one resistor and came over here? Or is it less than if we just had one resistor and came over here? Of course the resistance is going to be more. So the total resistance we expect to be more. And I guess what I could do is I could try to figure out what this total resistance is. But you know that the voltage total, well, let's see if we could do the voltage drops across each of these. If each of these resistors obeys V is IR, then we know that voltage total is... Well, it's going to be voltage 1 plus voltage 2 plus voltage 3. We can call it voltage battery or voltage total. I don't care what we call it. But the voltage total is, well, it's going to be the current in 1 times the resistance in 1 plus the current in 2 times the resistance in 2 plus the current in 3 times the resistance in 3. However, I1 is I2 is I3. So we can say that this is I times R1 plus I times R2 plus me times R3. I'm sorry, I just feel so awkward talking about I as if, oh man, it just doesn't work there. This, oh, I can factor out an I. I mean, I can factor me out. I mean, no, I can actually factor out an I. It's going to be R1 plus R2 plus R3 up in her. And then, wait a second. This statement says, well, this is the total current, right? This statement compared to that statement shows me that, wait, this says V battery is I times all those resistances added together. And this says V battery is I times the total resistance. So I can make the conclusion that R total, or R equivalent, is, well, add those suckers up. R1 plus R2 plus R3. And that's true for series resistors. So that's kind of a messy slide. Let's just go to this one. our total series equals the sum of all the resistances, and we've got to start from the first resistance and go up to the nth resistor. If you've got n resistors in series, that means you're going to have R1 plus R2 plus R3 plus R4, and you're going to go on and on and on, adding up until you get to R sub n. Cool? Now, what if you've got a parallel circuit? This is a little bit different game. Now I've got a battery, and I've got a resistor right here. But a parallel means there's another option for the current. So the current can also go this direction. And here's another parallel. Now I've got 3 resistors in parallel, and I've got R1 and R2 and R3. I could also, here comes a challenge for you. What is the same for all these resistors? Pause, figure it out. You know I'm not playing. Did you think that the current would be the same through each of these suckers? Well, not if R3 is a really small resistance. These could be whatever you want. If R3 is really small, all the current's going to want to go through R3 because it's not providing much resistance. Think about water flow. Water's got 3 paths that it could take. It's going to take the path with the least resistance. Nature doesn't like trouble. Nature's going to find the quickest way to drain capacitors, to drain batteries, all of these things. We got a plus sign here and a minus sign right here. And the cool thing is that all these guys have the same, they've all got the same voltage, because look at the potential difference between this side and this side. You know that this wire is an equipotential. So if you call this VBAT, my personal preference is to call that voltage 0, and this voltage right here is VBAT. Yeah, it is. And so that means that voltage right here is also VBAT, and there, and this voltage here is 0, and this voltage here is 0, and 0. These wires are equipotential, so everywhere here is the same potential, everywhere there is the same potential, so the potential across each resistor is equal, which means that I can say that, the current total is the current through 1 plus the current through 2 plus the current through 3. And I want to make that same statement I made earlier. I'm going to say the total is, the total is, it's going to be I total times R total. I'm going to try to find the total resistance or the equivalent resistance. And I know this I total right here is I1 plus I2 plus I3. And I guess what I need to do then is expand these in terms of, I know V is IR, so I'm going to solve this for I and say it's V squared over R. V, not V squared over R, but V over R. It's voltage across 1 divided by resistance of 1, plus voltage across 2 divided by resistance of 2, plus voltage across 3 divided by resistance across 3. And this would be true for any arbitrary number, but I like 3 because it's not 1 and it's not 2. It's also not 4, which would be too much of a bother. So this is my total current, and do you notice that each of these voltages ought to be the same? I hope that you do. My next statement is that, I total is simply V over R1 plus V over R2 plus V over R3. And then I can factor out a V and say it's V total, times 1 over R1 plus 1 over R2 plus 1 over R3. If I compare this statement right here to this statement right here, let me compare those two guys. This one says in its gory details, this one says I total equals V divided by, I total is V divided by R total. So hang on a second. These two things must be equal. This guy and, this guy right here. Yeah, this guy right here. Those two must be equal, which means 1 over R total is 1 over R1 plus 1 over R2 plus 1 over R3. Or if I were to make it in a nice, beautiful summary somehow, can I get a nice, beautiful summary? Yeah, I think I can make it nice and pretty. First of all, our total in series. To summarize our total for series, we found it to be the sum from thing 1, resistor 1, to resistor n of R sub I. But if I want the parallel, oh shoot, in parallel I have 1 over R total in parallel is, well, I've got to add them all up too. Let's see what I was doing right here. I was adding up R1 plus R2 plus R3, but the inverses of them. So it's I from 1 to n of 1 over R sub I. These act extremely differently. I want you to tell me what happens to the resistance of this circuit. Here's my first parallel circuit. What happens to the resistance of this circuit as I add more resistors in here? More R's implies resistance total goes up or down. Say goodbye to the orange marker. Bye, orange marker, you've been fun. All right, more resistance, more resistors in series means our total goes, well, naturally it goes up. It's harder and harder to get through, right? But what if I've got myself a nice circuit over here where I'm adding resistors in parallel? So here's a resistor in parallel, and here's another resistor in parallel, and here's another resistor in parallel. And my question is, more resistors implies that our resistance goes which way? Which way does that resistance need to go? As I add more and more parallel paths for the current to take, it's like opening more lanes on the highway. I'm going to get more flow going through. The resistance, in fact, drops as I add more parallel resistance, and it increases as I add more series resistances. That's because there will be less current as I add more and more resistors this way, and more current as I add more and more resistors this direction. In principle, you can combine series and parallel in a lot of beautiful ways, and we will study that, but not right now. Resistors will be, ha, you thought I was gonna tell you? No, figure it out. What's the same for all three resistors? Okay, so if that is the same for all three resistors, we can write the following statement. Now, that's cool. If, nope. What about, nope. What about, yeah. All right, I'm gonna set you up with a battery. There's my battery, and I've got some resistors. Yep, I'm gonna have 3 of them. See how hard it is for the current to get through those resistors because they're so bumpy? So I've got resistor 1, and resistor 2, and resistor 3. And over here, I've got the voltage of the battery, and there's probably going to be a current as a result. Because there's no way for current to back up in any of these suckers. You're gonna have the same current going through this one as you do through that one, as you do through that one, because they are in a series path. They're in a series path, so the current going through them has to be the same through each one of them. If I were to write a little bit of V as IR, are you ready for some V as IR? Here's what I'm gonna say. I'm gonna say that V, what is the same for all 3 resistors? Oh, you thought I'd just go on, did you? Huh, no. What is the same for all 3 resistors? Figure it out. I'm really not gonna tell you. You have to figure out what is the same for all 3 resistors. Oh, good job. Right, the same for all 3 resistors, since I've hooked everything up. My question is, this is our question to start off the day, what is the same for all 3 resistors? These resistors are experiencing one thing that is the same, and I want you to find out what it is. So, pause, figure it out. I'm seriously not going to go on until you think about it.